Welcome to Electrons, a discussion on periodic table trends. So, let's get started. First trend we're going to talk about is ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. If you move them sequentially, it costs more and more energy, as we've seen so far in our learning. And this written expression here is the ionization of element X in its gaseous state. Notice just one electron came off. Typically, when we do ionizations, it's going to be one electron at a time. So it's a measure usually in kilojoules per mole that tells us how much work is required to remove an electron. Also tells us how tightly the electron is held by the nucleus of the atom. I'm grabbing a pen. Hi. It depends on the nuclear charge, or the Z effective nuclear charge, and the average distance of the electron from the nucleus. Notice this is average distance. We know that an orbital is a 90% probability of finding an electron, and the distances aren't perfect. Okay, the energies are perfect, but the distance from the nucleus is not necessarily perfect. It's also known as the lowest energy valence electrons. If we say just ionization energy, usually mean first ionization energy. When we start to apply energy to an atom, the lowest energy valence electrons are the first to go. In other words, the most valent, the ones furthest from the nucleus, the ones of highest energy. In other words, they possess the most energy. It requires less to get them to leave the atom. As you strip electrons one by one, successive electrons take much more energy to remove because the atom now has I don't want to say just has a positive charge, but has a different construct. There's less repulsion in the valence shell, and therefore you have attraction overwhelming, and your atom tends to be smaller with greater Coulombic attraction for what is in the valence shell. We notice on the periodic table of successive ionization energies that there is a significant jump to go from a valence electron to a core electron, from one energy level to the next, and that's because there's a great reduction in radius. And that's reflected in the second IE for sodium and the third IE for magnesium being much higher than the previous ionization energy. And fundamentally, core electrons are going to be held much more tightly than valence electrons because the radius part of the Coulombic attraction expression is getting smaller, which makes energy in that relationship much greater, which means the bond is tighter. So here's that example, and if you notice, this is I1, I2, I3. These are the successive ionization energies. And here's sodium jumping from 495 to 4650 in its first ionization energy. Here's aluminum from 27 to 11,006. And this stair step takes you from valence electrons to core. And you can see that the jumps are huge, and it's reflective of what we've been talking about. First ionization energy generally increases going from left to right across a period because of increasing Z effective nuclear charge. That doesn't mean it's perfect. IE decreases going down a group because electrons being removed are farther from the nucleus and are well shielded from the nuclear charge. You want to mention repulsion when you discuss shielding. Okay, very important. Exceptions to these general trends occur at group 13, but also group 16. And the very brief reason here is shielding a p electron by s electrons. That's an oversimplification of the fact that there's a lot of repulsion that overcomes the added proton in the nucleus. And the same thing is true in group 16, going from 15 to 16. You're going from P3 in group 15 into adding in an oppositely spinning electron pair, increasing repulsion significantly from, for example, nitrogen to oxygen. Those are the exceptions to the IE trend, and they're visible in data. We'll see those in a second. Atoms with a low ionization energy tend to form cations. These are metals during reactions, whereas those with high ionization energy, with the exception of noble gases, tend to form anions. Sort of old news there. And this is the trend for ionization energy for each period. If you go up this, you notice you're in period 2, then period 3 here. The trend breakers are that going from S2 to S3 position here, S2 to S3, sorry, S2 to P1, wow, and then from P3 to P4 in the P sub shell. You see that the little break in the trend, and that's true for those for those, and then it becomes much more dramatic here when you go from D10 to P1. But you also see some leftover of the P3, P4 trend here, and it becomes much more dramatic in the D subshell going to the P subshell, and you sort of lose the trend as you go down the periods. But you always want to look for exceptions and try to ask yourself why that is. Why do these things happen? And obviously, the case has to do something with an increase of repulsion in the valence shell that makes those electrons easier to remove. Here's some numeric data to go with the images, and it just shows you, here's our S2 to P1 anomaly, and here is our P3 to P4 anomaly, where you see a stepwise decrease in ionization energy. And obviously, as you go down groups, it's going to soften the trend, but it's there. So when asked to explain periodic trends in the AP test, simply stating that trend increases or decreases across a period or down a group will not get you credit. You must clearly state reason and focus on forces. If two elements or ions are given and you're asked to compare a property, you must discuss both elements and both ions to get full credit. You can't just say strontium is going to have a greater first ionization energy. You need to discuss why, and you need to discuss strontium and rubidium, and make sure that you're being clear about each component. Electron affinity is a very important trend that sort of is the opposite of ionization energy. It is the attractiveness or the willingness of an atom to add an electron, okay, in the gaseous state. And here's an example of that process in chemical reaction form. If that addition is exothermic, EA is negative, and this is a sign of something, an attractive process. Remember that favorability, you want to have an energy that's negative. So the more negative, the more greater amount of energy released, and the increased probability. And so you sort of imagine in your mind which atoms would be most likely to gain electrons. And going down a group, activation energy generally becomes more positive, where less and less energy is released because electrons are less attracted to the nucleus because of the significant difference between the positive point charge. Distance, not difference. There are many, many exceptions to EA. It's not a great trend, but we can look at some data that will help iron out what we're talking about now. Going across the period, as atoms become more non-metallic, they tend to be more attractive to atoms because they have a greater Z-effective nuclear charge. So here's some data to support that. Here's the more negative going down the y-axis here, an atomic number increasing to the right. You see our greatest exothermic electron affinity are fluorine and chlorine. And you notice that as you go, this is hydrogen, lithium, boron, then carbon. This is going across that period 1 and then 2. And then sodium, aluminum, silicon, phosphorus, sulfur, chlorine, period 3. And then potassium and calcium. Like I said, it's not a great trend, but you see things that you would expect to be very attractive to electrons, so significantly negative electron affinities. We don't need to go much deeper than this to try to explain why chlorine might have a greater exothermic electron affinity than fluorine. Suffice to say that they are both quite negative. Next, let's talk about radius. Radius is one of the most obvious trends we solidified pretty well in introductory chemistry. We find atomic radius by measuring the distance between atoms in chemical compounds. When we take a diatomic molecule, we measure the distance between nuclei, and that is 2 times your radius. Typically, radius decreases going left to right across a period because of increasing nuclear charge. Increases going down a group because of larger orbitals and repulsion between electron orbitals and shells of electrons, also known as shielding. Nuclear charge stays about the same down a group because of the shielding. So this is an example of radius going left to right across periods 1 through 6, and we're ignoring the D block elements here because there's some phenomena we'll talk about later with that. Notice that the radii are pretty consistent in their progression and size. Your largest elements are going to be your elements and metals, pardon me, in the lower or the higher energy levels. General trends to periodic table trends: metals have low ionization energies, and nonmetals have high ionization energies and very negative electron affinity. Density is a trend that gets discussed from time to time. Generally, and this is a very general trend, it's not ironclad, generally increases going down the periodic table because atomic number increases faster than atomic size. So the density will increase, generally speaking, going down in groups, with the most dense elements tend to be in the transition metal block. Transition metal size contraction. This is an important one. The variation in size of atomic number increases across a row of transition metals is much less than among representative elements. In other words, groups 1 and 2 and 13 through 18, you see pretty dramatic increase in size or decrease in size across a period, whereas across the transition metal block, you don't see that. This is because electrons are being added to an inner shell, the 3D subshell, or 3D shell, pardon me, in each energy level. And so here's a diagram going across the D block. If this is ignoring calcium, potassium here, this is ignoring the representative elements and focusing on the D block, you notice the radius change from scandium across to arsenic is fairly small and very subtle. But it's still there. You can appreciate the fact that it's decreasing. Inner shell electrons are almost completely effective at shielding outer shell from the nuclear charge, so the outer electrons experience only a small and gradual increase in nuclear charge. The lanthanide contraction is even more dramatic. It's a similar phenomenon in the inner transition metals, specifically the lanthanides. They fall between lanthanum and hafnium, starting with 5D and cerium. In the 6th period, we have a much larger decrease in size occurring between lanthanum and hafnium because of intervening lanthanide elements. So let's talk about those. This additional decrease in size is called the lanthanide contraction. It causes hafnium to be the same size as zirconium, even though hafnium contains as many more massive particles, many more passive particles than zirconium has. So let's look at that. The graphic's not great, but this is moving across lanthanum all the way across to ytterbium. Okay, now keep in mind, this is zirconium right here, where I'm hovering. So even though our F block is way down here, the size isn't that different. Okay. The remainder of transition elements in the 6th period are nearly the same size as the elements above them in the 5th period. This causes 6th period transition metals to be extremely dense. This even influences lead and bismuth beyond transition metals, and lead and bismuth are down here. So this I don't like, but there you go, so just ignore it. That leaves us to video 4. So I hope this video helps you with your understanding of periodic table trends. Please come to class with questions, and we'll see you there.